Hi guys, in this handout we will look at benzylic chemistry. Now, as we saw hopefully in Organic 1, the benzylic position is a carbon that's bonded to an aromatic ring. And this carbon is a great site to form a carbocation because of resonance with the aromatic ring. It's also a great site to form a radical. We should have seen benzylic radicals in Organic 1. Now, we are moving away from the aromatic ring here, and we're doing chemistry at this benzylic site, benzylic carbon. So we're taking a little detour from the aromatic ring here. After we look at some benzylic chemistry, we'll go back to reactions, some more reactions of the aromatic ring. Now, this handout will be doing two types of benzylic chemistry. One is benzylic bromination. All right. It is a radical reaction. We actually looked at this in Organic 1, but we really didn't focus in a lot on the fact that it was an aromatic compound and the benzylic site, although we did use that term. We noted that when you do radical halogenation, that bromination is the most common because the thermodynamics are the best. Occasionally you may see radical chlorination at the benzylic site, but on small scale in the research lab, the bromination tends to be much more common. And you rarely see radical iodination or fluorination. Those reactions have problems thermodynamically. They're either too exothermic or endothermic. So we'll look at benzylic bromination. The other topic in this handout is benzylic oxidation. Also a radical reaction, but that'll be brand new chemistry. But we will use the big three oxidants that we saw during test 1 with oxidation of alcohols. Okay, let's look at benzylic chemistry or benzylic bromination. And toluene is going to be kind of a simple example of a aromatic that contains a benzylic carbon. If you take toluene, react it with elemental bromine, diatomic bromine, with some light energy, we can replace one of the benzylic H's with a bromine. So it is a substitution reaction. And by the way, the benzylic chemistry we'll be looking at here, either bromination or oxidation, these reactions require at least one benzylic hydrogen to be present for either reaction to take place. We will clarify that later. As another example here, if we take this compound, this propyl group, of course this is the benzylic carbon here. There are two benzylic H's. We can replace one of those with a bromine. We could use the same reagents here, but we also should know that we can use, instead of Br2, we can use NBS. Structure shown here, NBS, as we saw in Organic 1, is an alternative source of bromine radicals. I'm showing here light energy, or you can use benzoyl peroxide. Okay. Benzoyl peroxide. This is your peroxide, which is your OO. If these were two H's here, that'd be hydrogen peroxide. Instead of H's, we have benzoyl groups A benzoyl is a type of acyl. Okay, that is an acyl group, but if it's just a benzene, it goes by the name of a benzoyl. And benzoyl peroxide can also be used instead of light energy to promote formation of your bromine radicals, either from NBS or from bromine. You may be familiar with benzoyl peroxide in the from the drugstore, because it is used as a an ointment or cream for the treatment of acne. The peroxides will kill the bacteria. Okay, let's review our mechanism for this radical bromination. I'm just going to use elemental bromine. If we have some light, that light will shine onto the bond and provide energy, and it will cause the bond to homolytically cleave. One electron goes one way and one electron goes the other way. And whenever we move a single electron, remember, we use a fishhook arrow. Okay? We don't use a double-headed arrow or pointy arrow, or whatever you want to call that. We use a arrow like that. It's called a fishhook. And this mechanism, promoted by the light or the benzoyl peroxide, forms a bromine with 3 lone pairs, but also 1 single electron. On one side, the other side would be the same exact thing. Okay? Instead of redrawing that, can I just show 2 here? And I believe I call this heterolytic bond cleavage. It's actually homolytic. Homolytic. Because each bromine gets the same result. Each bromine gets a single electron. All right. If we had taken maybe something like HBr, and these electrons went, okay, I'm moving both of them, so I'm using a regular arrow. And this is a progression arrow. This would give H+, that is no electrons, and the Br would have taken on not 1 electron but 2, and that's a minus charge. And this is different outcomes. One bromine got 2 electrons and the H got no electrons. So that would be heterolytic bond cleavage. Here we did homolytic bond cleavage. And here the bromine is negative. Here this is a radical, but it's also neutral because it's owning 7 electrons. Alright, so a little review. Now at this point, we can bring in our molecule with a benzylic CH. Let's draw these H's out. I'm doing toluene here. And one of these electrons will actually kind of come over here and bond with one of these electrons. One of these will come here. Okay. How is this actually going on? There's some magical bonding going on here. This is the best we can show in terms of mechanism. Sometimes people say that this bromine radical will strip away an H. Basically, you know, real mechanism of what's happening here. Does one electron just break away from carbon and go team up with the bromine radical? Effectively, yes. But how does that actually physically happen? Well, we're not really showing that. I don't know that I can explain it. You might be able to look into it. But one electron teams up with the bromine electron. The other electron moves on to carbon. And that gives a carbon with just 2 H's and 1 electron. Plus what? What did we just make? We just made HBr. All right. And so this, if we balance this reaction up here, it does give HBr. Now we made a benzylic radical. It's also resonance stabilized. All right. You can do resonance of radicals. I will do one resonance structure. Here's a pi bond. I'm going to consider the outer line here, the pi bond. This electron moves in here and teams up with one of these electrons, and the other electron in this pi bond moves on to carbon. And we can get a new Lewis structure, which we call a resonance structure, that looks like that there, right? 2 electrons teaming up to make a second bond. It's going to be a pi bond. And the other electron in this original pi bond moving back onto carbon to become a single unpaired electron. Radical. Note that there's no charge here. All right? There will be no charges anywhere. This is not an ionic mechanism. It's a radical mechanism, and usually they are not ionic. Neutral radicals. We can keep going. 1 electron from the pi bond can team up with this one and make pi bond here, leaving the radical here. All right, I'm not going to keep going there. I did sort of make my drawing here complex by showing my arrows for the resonance. Next step here. All right. Now, we do have a second bromine radical. We could team up with this radical and make our product. But instead, let's bring in a second molecule of bromine. All right. Forget about these mechanism arrows here. This radical teams up with bromine here. 1 electron from the bromine bond teams up with this 1 electron to make a carbon-bromine bond, and that gives our product. All right, I'll just draw the benzene ring as a phenyl. I'll just draw it just like this here. That plus what? We really need to move the other electron onto the bromine. Plus Br radical. There's your product. But by reacting with another molecule of bromine, we get product, but we reform another bromine radical. And it allows for propagation. That is, this, it's almost like catalyst recycling, but it's not catalyst. It comes over, and then we can do another cycle, because every cycle you come through here, you'll make a bromine radical. Now, anytime you see NBS, it's the same mechanism. The beginning is the nitrogen-bromine bond does a homolytic bond cleavage. 1 electron goes one way, 1 electron goes the other. You get your bromine radicals. You also get the it's actually a nitrogen radical. And it actually turns out that the nitrogen radical is what initially strips out an H. Okay? So one electron here, one electron here, the other electron onto carbon, and you see that we would end up with our benzylic radical, but plus what? You would end up with this molecule here called not N-bromosuccinimide, but just succinimide. And usually it will precipitate in the reaction. Where if we use just bromine, we will get HBr. Now HBr will typically be a gas, and sometimes you can see that gas coming out of your reaction. If you hold pH paper above your reaction, it'll turn red. HBr is an acid. Succinimide is really not a strong enough acid to give a pH indication. But it does typically precipitate because it is a solid, and it tends to be insoluble. Okay, that's radical halogenation. We can do it with other substrates as long as there's a benzylic hydrogen. Why would we want to put a bromine on a benzylic carbon? Well, it gives you other chemistry you can now do. For example, we could react this with potassium cyanide, and we would expect here to do an SN2 substitution. And the cyanide could displace the leaving group. We added a leaving group by doing a benzylic bromination. Or if we react with potassium tert-butoxide, this looks like a sterically hindered base. This looks like a classical E2. And it looks like we'd probably be looking to make this alkene. So, putting the bromine on the benzylic carbon opens up additional chemistry that can be done. Here's a multi-step synthesis that you can try. All right. I need to be able to recognize what's going on with each reaction. And number 4 looks like NBS and light energy. Looks like maybe a benzylic bromination. Okay, you can think about that. You can do that for homework. On the flip side here, this shows a synthesis of the drug anastrozole, which is used to treat breast cancer. And they actually pick up here at 19, and you have this sort of doubly benzylic bromide and potassium cyanide. They're actually doing a double SN2, like we just showed here. They're using a little phase transfer catalyst. It looks like it's biphasic. You can look at the conditions, but the main thing is here the cyanide and the SN2. Then they're doing really more SN2. Hydride's acting as a base, and they're making an anion here, and then reacting that with methyl iodide. And this anion is attacking the carbon and kicking off the iodide. That's how they get these methyl groups, but they actually do it 4 times. Because you can actually remove each H and then add the methyl group as we did 4 different times. That's how they get here. But from here, look what they're doing. They're doing a benzylic bromination. Benzoyl peroxide, NBS. Carbon tetrachloride is a common solvent for radical brominations. And you see that they're doing a benzylic bromination at the only remaining benzylic carbon where there is a CH. Now, both of these are benzylic carbons, but there's no benzylic H there, and so you would not expect any benzylic chemistry because, again, the benzylic chemistry we're doing here requires at least one benzylic H, yeah? From there, they then remove this bromine. Let's put some lone pairs here. 2 lone pairs. This nitrogen anion kicks off that leaving group, and that's how they get this triazole ring bonded to the benzylic carbon. So, several SN2s, yeah? Lots of classical chemistry there. Textbook introductory organic chemistry. Okay, the next reaction we'll do, the other benzylic reaction, is benzylic oxidation. Now here, if you have a benzylic carbon with an H, and you react it with one of the big 3 oxidants, remember those? KMNO4, also chromium trioxide, or sodium or potassium bichromate or dichromate. Any of those 3 will oxidize this carbon all the way to the benzoic acid. Now, of the 3, potassium permanganate is by far the most common with benzylic oxidations. Now, we're not going to look at a mechanism here, but it's probably radical oxygenation. And probably what's going on here is all 3 H's of the carbon are replaced with oxygens. And it's going to be OH groups. Now, we could actually do that over here. If we react this with, okay, this is 1 equivalent. If we react this with maybe 3 equivalents, we could replace all 3 H's with bromines. But with bromination, it can be selective. Here, it's typically not going to be selective when we replace all 3 with oxygens. But now, this molecule is not stable. It will lose water and that's how you get the benzoic acid. This type of mechanism, losing water and forming a carbonyl, we'll actually look at when we look at carbonyl chemistry. So, that's actually what's going on here. We don't need to look any closer at mechanism. In the end, it's really just a predictive product. It's also pretty significant transformation. This saturated carbon becomes a benzoic or a carboxylic acid. Now, if you have more than 1 benzylic carbon and you do this reaction, actually you will cleave off all the carbons and just leave 1 carbon as the benzoic acid. And the other carbons will most likely be cleaved or end up as CO2. And that becomes a very kind of interesting reaction. This could be 3 carbons or maybe 20, and they would all be cleaved off and you would just be left with 1 carbon benzoic acid. Very neat reaction. I wonder who was the first chemist to observe this reaction, they'd be like, where'd the rest of my molecule go? Well, you must have lost it out the condenser as CO2, because we don't just magically lose carbons, or they don't just disappear. Okay. I'll let you try this one down here for homework. All right, these are really just predict the product reactions. I will add a question here. Why is benzene highly toxic but toluene less toxic? Well, benzene is very lipophilic, and it will localize in the fatty tissue in your body, and it tends to stay there, and then it starts causing problems. But toluene, having this benzylic carbon, is oxidized by the body. Now, your body doesn't use KMNO4 or chromium trioxide, etc. Your body uses enzymes, and your body is a lean, mean oxidizing machine. And it can oxidize this methyl group to the benzoic acid. Chemistry that we know we can do. The body can do it as well. Now, this carboxylic acid will tend to exist as an ion in the body, okay, given the pH of blood. And since it's an ion, it has pretty good water solubility, and thus the body can flush it out through the urine. And so because of this chemistry and the physical properties of ions that we should know, solubility of ions, toluene doesn't build up in the body like benzene does. And so having that methyl group there makes toluene less toxic than benzene. This methyl group is called a metabolic handle. It's something that the body can metabolize. All right, we can also use this new reaction in multi-step synthesis. And so for homework, or I could do this here, because we may need to do this diazonium in a next video. Yes, why don't we do this here, since we have a little time here. Little practice with multi-step synthesis. From benzene, okay? If you want to pause the video and try it on your own. Basically, we want to assess this, though. Both of these are meta-directors. The nitro group and the benzoic acid are meta-directors. So if we back this up to, say, nitrobenzene, doesn't matter where I put it, it's nitrobenzene. How would we put a group para? We're not going to be able to put a group para. If we back this up to benzoic acid, how are we going to be able to put a nitro group para to the carboxylic acid? Can't be done. So we really don't want to consider coming back to these two. At this point, we want to consider, are there precursors to any one of these groups that are ortho-para-directors? We need a para-director at some point. And indeed, a precursor to a carboxylic acid here on the ring is an alkyl group. And so I'm instead going to back this up to and envision maybe something that looks like that. And at this point, I'm going to start coming forward and show what I'm talking about, because if I have that and I do a nitration now, see, this is going to become the carboxylic acid. But at this point, I do my nitration. It's an ortho pair director. Now I'm just going to show pair because that's what I want. I'm also going to get ortho. I'll have to purify that out. But when you're doing multi-step synthesis with ortho pair directors, you're going to have to purify the other isomer out. But I can go there. Now I can come to my product. If I treat this with KMNO4, all right, usually a little water to help dissolve things, and it's heated. That will oxidize this to the benzoic acid. We will lose a carbon-carbon bond cleavage, yeah. Now I can back this up to benzene, but it's best to back this up to the acyl group. And coming forward, I would use like the Clemenson reduction, and then back this up to benzene. And coming forward, I would use something like this, a Friedel-Crafts acylation followed by reduction. Remember, this is the better route to make an alkyl group on the benzene ring because it avoids polyalkylation and in some cases rearrangements. You wouldn't really get a rearrangement here with an ethyl group, but it avoids polyalkylation, so it's always best to do a two-step route to an alkyl. While we have the alkyl group there, that's when we do the nitration, because it's an ortho pair director. Then we convert our precursor to our carboxylic acid using this new oxidation reaction. Okay, so there's an example of using this chemistry in multi-step synthesis. Okay, we'll save the diazonium reaction for the next video. It's called a diazonium reaction, sometimes also called a Sandmeyer reaction, after the chemist who developed some of these reactions. We'll also look at, in that next video we will look at diazo coupling reactions. All right. Then also in this handout is more of the multi-step synthesis. Here. Okay guys, we'll end this video here.